this is just like a little bite-sized stuff you should know.
That's exactly what it is. It's like Snickers miniature, but of stuff you should know.
That's right. Now, you know our love of small things here.
Especially Snickers.
Or like tiny Tabasco bottle version of our show.
Those things are priceless.
All right, so physics, dark matter, go. Let's do this.
All right, so
this wasn't as hard as I thought.
No, and it's actually pretty easy to get across.
Yeah.
Here's the thing. So astronomers have gotten to the point, it's starting in about 1920 on.
Yeah.
Astronomers and physicists and astrophysicists and even particle physicists got to the point where all of their combined knowledge was refined enough that they could look out into the universe and be like, we can figure out how much this weighs.
Right.
To put it more scientifically, we can figure out what the mass of the universe is. It's going to take us a really long time, but we are now at the point where our level of observation and our level of understanding of physics is such that we can do it. We're there now.
Yeah, and it's not just like, oh, well, that weighs this, the end.
Right.
Like, knowing something's mass tells you a lot about it, the way it behaves.
And the nature and future of the universe, as we'll see.
Yeah, for sure. So it's not just weight. It's more complicated than that and what weight can tell us.
Right. The problem is you can't just like put a galaxy or star or something on the scale.
They tried.
They have to, it broke the scale pretty quick. It actually vaporized it. But there are ways you can infer the mass of something.
Yeah.
One of the ways that you can infer the mass of a star, from what I understand, is to measure its luminosity, how bright it is.
Yeah.
I've also heard that's a mixed bag, because
it seems like it from doing this.
They have different sizes in their lifespan.
Yeah.
I've just heard luminosity and mass is not just straightforward.
Sure.
Like most things in astrophysics are.
Yeah, that's the word on the street.
Right. So when they started getting to the point where they could infer the weight of a star or of a galaxy or of a galaxy cluster, which is basically like a galaxy of galaxies,
yeah,
they started to notice something really weird. All of the matter that they could see, the stars, the gas clouds, the cosmic dust, the everything, matter, things that make up you and me, things that everything has a common basic unit, an atom that is made up of elementary particles like protons and neutrons and electrons, matter.
Every non-living and living thing in the galaxy,
you would think, is made of matter. The problem is they started finding that, this galaxy over here and this galaxy cluster, and everywhere we're looking, the amount of matter that we're seeing is way too small for the amount of mass that the thing we're looking at appears to have. And a cosmological mystery was launched. What the heck is going on was the question of the day.
Yeah, so all of that matter that we know about, they call that baryonic matter. And they were like, the calculations are all for something, like there's got to be something else there to account for this.
Well, that's the two possibilities.
Well, sure. And so way back in, was it 1932, an astronomer, a Dutch astronomer named Jan Hendrik Oort, because he's Dutch.
Sure.
He actually, I believe, was the first person to use the term dark matter. Is that right?
That's what I saw.
So dark matter is a sort of a placeholder name for what they came up with for this, for lack of a better word, this invisible matter that has to be out there. It's sort of like wind. Like, you can't see wind, but that doesn't mean it's not out there, because you can measure it in different ways, see how it reacts on other things.
Right.
And so they started calling it dark matter.
Right.
This invisible. Well, we'll talk about what it ends up sort of looking like in a minute. I won't give that away yet.
Right.
But this invisible matter
that they think is there.
Right, but it doesn't emit or absorb light or electromagnetic energy. So it's way different. It behaves differently, such that people were very confused as to what the heck was going on.
And they still are.
Yeah, sure.
So this term dark matter, like you said, it's a placeholder. It's a placeholder for the current point we are in our understanding of the universe, which is when we look out at galaxy clusters and galaxies and all this stuff, there's not enough matter to account for the amount of mass that we're seeing. So again, that means one of two things. Either there's something there that we can't detect, or our understanding of physics is off. And the term dark matter stands for both of those. It could be a thing, an undiscovered particle or something like that. Or it could be a misunderstanding of physics that we need to eventually correct. Either way, there's a lot of mass that is unaccounted for throughout the universe. And it seems like there's a lot more what we call dark matter than there is regular matter. And the more we look into it, the more it seems like there's something there that we haven't discovered yet.
Yeah, so right now, baryonic matter, all the stuff that we know about, counts for about 4.5%. 23% of where they peg dark matter. Then we have something that I don't even know if I ever want to cover called dark energy, which makes up the other 72%. But they know it's there because there's something out there that we can't account for that has a significant gravitational force.
Right, that's where the whole thing started, where they first detected it.
Right.
So when they first started looking out at galaxies and stuff like that, there's this whole thing that Newton came up with, the second law of motion.
Yeah.
Where, and this is like a tried and true law. It's a law. This isn't Newton's suggestion of motion, or Newton's second, what about this of motion? It's a scientific law. That's how, that's as proven and accepted as a scientific observation can be, is to be made a law. And it said that when you're looking at a galaxy far, far away, and the most of the matter is accumulated toward the center of the galaxy, then that means most of the mass is accumulated toward the center. Okay?
Yes.
Okay. So that means that the stars near the center are going to spin, they're going to rotate around the galaxy a lot faster than the ones on the fringes, because the ones on the fringes are going to go a lot more slowly because they're further away from that center of mass, so the gravitational pull is going to be weaker.
Yeah, I mean, that's the easiest way to say it, is in the center you have more mass. More mass means things are spinning faster, there's more gravitational pull.
Right.
So all the astronomers suppose, like you said, the stuff on the outskirts are probably hanging out there spinning a lot slower.
Right. Well, when they looked, they found that's not the case at all. As a matter of fact, the stars on the outside are spinning around the center of the galaxy just as fast as the stars near the center of the galaxy, which makes zero sense.
Yeah, it's almost as if there's some invisible force out there.
Right. And like if you look at this this galaxy, the situation that they started to find, and it wasn't just one galaxy, they found it in this galaxy too, in this galaxy too. And even stranger than that, they found it in those clusters, those galactic clusters. So rather than stars that make up a galaxy, this is galaxies making up a huge giant mega galaxy. The same thing happened. The galaxies on the outer edge of the cluster were circling just as fast as the ones toward the center. And it just must have knocked their socks off. I can't imagine how many times they went over the same formula to make sure that they had gotten it.
This is for clarity. This was the 1950s and 1960s is when they discovered.
First noticed this.
Yeah.
Okay. So what they figured out was that either there was something really wrong or there was something that they hadn't picked up yet, because those stars on the outer edges of the galaxy, or those galaxies on the outer edges of the cluster, for as fast as they were flying, they should have spun off into space.
Yeah.
There was something missing that explained what was holding that galaxy or that cluster together as fast as the stars of the galaxies were spinning around on the outside. That was the first clue that something was way up with that astronomy was missing something big.
Right, and they knew this was off because they had been using luminosity, like you said, to take measurements for years, and it was pretty good. But then when they started measuring the rotational velocity of things, like how fast something was spinning in relation to where it was, like toward the center, it like you said, there was a missing ingredient there that didn't match whatever these luminosity readings were showing.
So you're right. Luminosity was clue one. The angular rotation was, or acceleration of the outer stars was clue number two. So now we've got two different ways of measuring the mass and gravity of remote bodies in the universe.
And they don't align.
Our point, well, they're aligning in that there's something missing here.
Right.
And I think that's a pretty good cliffhanger for a breakdown too.
I think people are going to be like, what?
Yeah, well, why don't you guys go listen to the first half of this podcast, or first part again, and we'll see you after these messages.
Hunter Jesperson. He
and cleaned up his house.
And he said, "Oh, don't pay any attention to them."
I really hope we're putting this well. I feel like we are, but sometimes you just can't tell.
No, this isn't the Sun Redux.
I hope not.
No. This is much more simple.
Okay.
So, like you said, they not only studied regular galaxies, but they started to study what you refer to as, and you didn't make it up, but galactic clusters. These knots of galaxies, could be thousands of them, could be hundreds of them, but they are bound together by gravity, and they were like, you know what, let's study these, because maybe what we can find, or this is what we suppose at least, is there might be these big giant pools of hot gas that we never could detect before, and that would account for all of this mass. Giant pools of hot gas that we never could detect before, and that would account for all of this mass.
Right.
And they did find these superheated gas clouds, and we're like, great, that's it. And they're like, no, it still doesn't account for everything.
That's like a small percentage of what needs to be accounted for.
Right. So it was a breakthrough, but it wasn't the solution solver that they were looking for.
It was, because if you can find something that we know has mass, like huge clouds of gas, that again, a particle has mass, and if you put enough particles together, it has a lot of mass. If you could fill in the blanks of the missing matter that explains the mass of this thing you're looking at, great. Especially if it's something we already know about, like hot gas. And they did find some hot gas, but say that explained 5% of the missing mass. It did explain everything. And what that did do also was, okay, we've gotten that much more sophisticated, and it still hasn't answered this dark matter thing. It's pointing to the idea that there's something we haven't discovered yet that is accounting for all of this.
It's very foreboding.
It is, but it's also, I think, very exciting.
Sure.
Yeah,
for them and us. So the other thing that happened when they started studying these galactic clusters was that they found out that these clusters and superclusters can and this is really neat. You can look up images of this. It can distort space-time because their mass is so great. So if you're on planet Earth and there is a light, so you're looking from like a telescope on Earth, you're looking at a distant light, like who knows how far away.
Like a star 3 billion light years away.
Sounds great. In between you and that is a galactic cluster, let's say. That will act as a lens, and depending on where it's situated to where you are relative on Earth, it will distort that light into one of several things. If you're in perfect alignment in it, it's going to form what's known as an Einstein ring. And if you look it up on the internet, it's like this beautiful like circle of light.
Yeah.
It's really cool looking.
Yep.
It could be elliptical or oblong. They call it the Einstein cross. Basically splits it into four. So it just looks like four little stars all like perfectly aligned into one of several things. If you're in perfect alignment in it, it's going to form what's known as an Einstein ring. And if you look it up on the internet, it's like this beautiful like circle of light.
Yeah.
It's really cool.
Yep.
It could be elliptical or oblong. They call it the Einstein cross. Basically splits it into four. So it just looks like four little stars all like perfectly aligned into one of several things. If you're in perfect alignment in it, it's going to form what's known as an Einstein ring. And if you look it up on the internet, it's like this beautiful like circle of light.
Yeah.
Stars all like perfectly aligned.
4 copies of the same image.
Yeah.
Yeah, and like a cross.
Yeah, perfect cross. Or it could be a cluster, and this one is sort of cool just because it's like kind of scattered. It looks like a bunch of like arcs and banana-shaped arcs and arclets.
But it's all different versions that
Right.
you're seeing, and what you're seeing is that faraway star, but you're seeing through that galaxy cluster.
That is a distortion of space-time.
Right. That the mass of these clusters are so big and so huge that the gravity in them bends light.
Yeah.
Just like a mound of glass can bend light.
Yeah, like
Optically.
a magnifying glass.
Same thing. Now, we've gotten to the point where we are so good at math and physics that we can look at that reflection, that bend,
Yeah.
and say this galaxy has that much gravity, and since this galaxy has this much gravity, it must have this much mass.
Yeah.
Now, if you take that number, this much mass, and you examine the luminosity of the galaxy,
There's that difference.
yeah, you're like, this is like not off by, like the luminosity is 10, but the mass is 10 and a half.
Right.
There's like sometimes factors of like times 100.
Right.
Sometimes, like, there's just no way that your math is off. There's a huge discrepancy. So there's a third clue that there's something missing.
Yeah, I mean, that's basically all these are little hints along the way that we're still not able to account for something with our calculation.
Yeah, and rather than the better and more sophisticated our observations and exploration, how much baryonic matter we think that there is,
Like math.
go computer.
And they acted like this blue.
This is a clump. In other places, there were long and it looked like it had galaxies or galactic clusters trapped in a spider's web.
So cool.
But it just permeated everywhere. And like you said, it seemed to be like this cosmic glue or cosmic connective tissue. And it was pretty surprising. So they said, okay, well, that's the computer's take.
Right.
Let's see if we can replicate that. And that kicked off a series of projects that are still going on today to map dark matter in the universe. Which
Yeah.
I want everybody to stop for a second, because this is about as nuts as it gets. They have gotten to the level of sophistication where astrophysicists are mapping scopes that you walked around
Right.
and looked out into the universe on. It's amazing.
Did they let you take pictures?
Yeah, I guess so, with your phone.
Oh, I thought you meant, with the 340 megapixel
No.
camera. No.
I'm sure they were taking pictures. They didn't give them to us or anything. But what's crazy is it's on Hawaii, so it's just hot and muggy and
Yeah.
humid. And then you drive up this mountain and you're like freezing in a North
wow.
Face coat with like a hat on.
Yeah.
And then you just go back down the mountain and it's Hawaii again. It's
That's
very,
great.
very cool experience.
So what they did here was basically stitched all these photos together. It was like photos of 10 million galaxies in 4 different regions over 5 years. Stitched it all together, and what they finished up with was basically saying that computer model was pretty on target,
Yeah.
because what this looks like is what it spit out
Yep.
so many years ago.
Yeah. So they're definitely onto something, it seems like.
We take another break?
Yes.
All right, we'll talk about what dark matter is. Hint, we don't know.
Hi, I'm Jeff Krasno, and welcome to Commune, where every week we explore the wellness practices to ideas that inspire us.
All right, Chuck, we're back.
This is where I start to get a little brain breaky. I understood stuff, but this stuff is where I was like, what?
Well, we're transferring from astrophysics to particle physics.
Maybe that's my hang up.
And particle physics is hard. I actually had to teach myself particle physics to write one episode of The End of the World.
Maybe that's my problem.
It's and even still, I'm like, wait, what? It's really hard to understand.
Yeah, I've always been an astrophysicist, though, at heart, I think.
Uh-huh.
So that's just goes against my nature.
Okay, I'm with you. But they're very much tied together. Like, you need particle physics to explain these larger cosmic structures.
Right. So the big question here is, at the end of the day, is it the fact that we just can't really observe this stuff and it's just like all the other matter?